hopefully we won't have a visit today from any
Hi,
clients.
Marissa.
Okay. Yeah, does everybody want to say hi to everybody? I think we should. Never
Hi.
mind. I already have it set up. At
Veronica,
the end.
Bobby.
And did we miss anybody?
No, there's only 10 of us.
That's it. We're recording this for 3 people. Really? We just spent 10 minutes in production time for this? I know.
You can cut it out. We haven't started teaching yet.
Okay. All right. So here is my biggest thing. Did I tell you about the train for related rates?
No.
No.
Okay. Did you ever go to Monaco? Okay. And sit behind the BP and have to wait for a train to pass?
I know what you're
Anywhere?
talking about.
Okay.
Oh, okay.
So now let's say, how about anywhere? Did you? And if not, put yourself in that situation. But you have, right? Okay. So you're sitting at the train thing, okay, and you could see it from over there. Now here's the thing I want you to imagine. Your eyes are stuck straight ahead. You'll see why. You always have the questions, don't you? Okay, so the train's way over there, and my head is on the train. Now, do you realize trains have to go, they don't have to go to constant speed, but they will because they have to slow down to a certain speed. It's either 35 or 40 in a residential area. They can't go any faster than that. So let's say they're coming at a constant speed of 40 miles an hour down the track. If your head was on the front car, and again, your eyes can't move, okay? So your head's on the front car. Is your head going to be turning at a steady rate to keep your eye on that front car? Okay, so everybody
No. No. It's not.
What did you just...
No, because whenever you're over here, it's going to be slow, and then you're going to get up here, it's going to go
It's
faster.
just
and
a
it's gonna go
Doppler
slower.
effect.
Is that what that is?
Yeah.
Okay, yeah, right. So your head is turning like faster when it's right here.
Right.
You're turning the fastest to
Right.
keep your head on it. Okay, those are two related rates. The rate that the train is going is 40 miles an hour. The rate that your head is turning varies. So you want to say how fast is your head rotating when the train is 100 yards away? Or how fast is the train, or how fast is your head rotating when the train is directly in front of you, or whatever. You could say it by an angle that front car is away from you, or by a distance that the train is away from you. Either way, okay? That's going to tell you, this is when I want to know what my angular speed of my head is. Because, of course, that is the pressing question of everyone when they're sitting at a train. How fast was my head going? Right? Okay. So that is one situation of where two or more quantities, which are rates, okay? And rates are always your speeds, your rates of change with respect to time. How they're related and how one of them is changing at a constant rate and another one is going to be changing at a variable rate. And that's all that page says. So here's some examples, and those are the ones that are on your paper. So, move this out of the way. And then the steps that are on the back, I'm just going to highlight them as we do them, okay? All right, so somebody tosses a stone into a pond, causes, the ripples to start to form. So this is saying that the radius of the circle in the pond is increasing at a constant rate of 0.5 meter per second. How fast is the area of the ripple increasing when the radius of it is 20 meters? So again, you can maybe think of how fast the area is changing when that circle's really small. And then as that circle gets bigger, think of all that area around it, okay? So, and you can find this. Sometimes it's interesting to find it when it's 2 meters, and then when it's 10 meters, and then when it's 20 meters. And you can compare and see, I thought it was getting faster, or I thought it was going to get slower, or whatever. But so we're just going to find it at 20 meters. So the first thing that's always going to help is if you draw a picture, and we're talking about just the ripple, okay? Now, when you label this diagram, you only want to put things on it that are going to remain the same. Point being, is this ripple always going to have a radius of 20 meters? No. So just put an R on the radius. Now, rates are rates of change, which are derivatives, right? It's a rate of change of something. So that 5 meters per second that radius is changing, that's a rate of change of the radius with respect to time. Any rate of change of anything with respect to time is going to be like this, and then you want to think, okay, what is changing with respect to time at 0.5 meters per second? The radius, right. So I'm going to put an R for the radius. That R is not for rate. People who struggle with related rates problems in the beginning, maybe because this is always the first problem I do, put dr dt for everything. They go, oh, it's the rate. R is not for rate, R is for the radius. If I'm doing a boat problem and I use R for rope, still, coincidence, okay? It's just whatever variable you have here, the rate at which it's changing, use that variable, okay? And it's always with a dt on the bottom because it's always with respect to time. All right. You want to find, I always do find, how fast the area of the ripple is increasing. So how fast is another rate, right? What do you think I should put here? Good, yeah. So you want to know how fast the area is changing. When what?
When R equals 20.
Perfect. Yep. And if we use all these units too, not only will Mr. Haladio be very, very happy, but it'll help, it totally helps you with the correct units for your answer. Okay, so we need now an equation that relates A and R, and then we're going to differentiate that equation with respect to time, and then we're going to be able to use all our given information to solve for what we want. Sound easy? Okay, so give me an equation that relates A and R. Okay. Now for these formulas, you can use, if you ever forget anything, like the volume of a cone or something, they're in the front cover of your book, Google it, ask me it, whatever, okay? All right, so now we want to, again, differentiate that with respect to t. So it's like implicit differentiation. So the derivative of a with respect to t right, because the derivative of a is 1, right? And the variables are different, so you need your dA dt. So it's just like when you were differentiating a y term with respect to x and you needed a dy dx. Okay. All right, how about the other side? And then?
dr dt.
Yeah, good. Because again, you're differentiating an r with respect to a t, so you're going to need your dr dt. Oh, now everything's almost done. You have something to plug in for dr dt, you have something to plug in for r. Let's put the units in with it too. So when r is 20 meters, dr dt is always 0.5 meters per second. 2 times 0.5 is 1, so 20, yeah. What are my units? Perfect. And if you didn't do the units all the way through, if you weren't paying attention, but you were going to then come up with the units when you were done, which is not something Mr. Haladi would be proud of, but, I mean, it's a rate of change of area, right? Area is given in square units, and it's a rate, so it's going to be over time. Okay, so it would be square meters per second. That's a related rates problem.
That is cool.
Isn't it? Oh, that's like the one we did for Jeopardy. We did something. Something like that. So you draw a picture. You label the picture. If you want to flip your papers over, see these steps should match up. Yeah. You're going to label the picture with all of the variables that are relevant to the problem. Only put numbers on the picture, and sometimes we will, but only if those numbers remain constant. If something is always like 5 miles high or 5 kilometers away or something like that, then put a number on it. But if it doesn't remain constant, don't put the number on the picture. Write all your given using proper notation in units. So our given rate was dr dt with the units. And then what we wanted to find, write the notation for the unknown rate. What we wanted to find was there, and this was more given information. Okay? write an appropriate formula. It's usually going to be geometry, like this one, a trig formula, proportions, Pythagorean theorem. Okay, it just depends on the picture you draw. That's why the picture's key, okay? Because then you'll be like, oh, well, I guess it's a Pythagorean theorem, just by looking at the picture. Write a secondary equation if necessary. If your first equation is something like v equals pi thirds r squared h, what did I just give you the formula for? You may know? Close. Because, yeah, cone, because I put the thirds on it. So if I didn't have the 3 on it, it would have been volume of a cylinder. If I have too many variables, I'm probably going to have to get rid of one. So they're going to give me some other information where I can write a secondary equation and knock out one of those variables with a proportion or something. So we didn't have a secondary equation in here. Differentiate both sides with respect to t. We did that. Substitute in the given information and label your answer.